Alright, continuing our series. Reactance is a property of coils and capacitors. They're signified by this X here. X is reactance. X sub L is a reactance of a L, as in Henry's, for an inductor, a coil of wire, and X sub C, C for capacitors, which is, of course, in farads, but as opposed to X sub F for farads, we just use X sub C for capacitors. So, as you see, the reactance of a coil, X sub L, is equal to omega L. And as we recall from earlier, our previous video, omega is 2 pi f, where f is the frequency in hertz. 2 pi is simply a constant value of 3.14. That's pi, well, rounded up for practical use. Multiplied by 2. 3.14 times 2 is, of course, 6.28. Just remember, 6.28. You're going to use that a lot. And this is, of course, with alternating current circuits, a sinusoidal waveform. So just remember, your omega is always 2 pi f, 6.28 times whatever your operating frequency is. That means the reactance of the coil is going to change depending on the frequency, how many cycles per second the alternating waveform has. And L and Z is your capacitance, as we just reviewed. Schematic symbol for a coil, symbol for a capacitor. Reactance is the magnitude of your impedance. And your impedance can be thought of as the AC equivalent of a DC resistance. And the units of your reactance are in ohms. And for circuit analysis, reactance lets us treat reactive elements, capacitors and coils, like resistors, plus or minus theta, which is our angle, which comes from our impedance. So remember, all that impedance is reactance with an angle, which we reviewed previously in complex algebra, how to get our angle. And of course, here is where we come to how things like television signals, radio signals, and Tesla coils function, and that is by the property of resonance. So, resonance for an RLC, or resistor, coil, capacitor circuit, occurs when the state of the reactance of the coil, X sub L, is equal to the reactance of the capacitor, X sub C. So if X sub L is known, if we know what our reactance of the coil is, then the matching capacitance for the resonant condition is C equals 1 over omega times our X sub L. And this would be for a series connection. Also sort of for parallel, but we're going to get to parallel connections later in this video. And of course there is a resistance in the coil, because it's a coil, a length of wire. There is some DC resistance called the Q factor, which we'll get to in a bit. And our but in a very well-made coil, the Q factor is often so high that it affects the resulting part values very little. So you can just go with these simple formulas for most cases for high quality coils. So getting back to your capacitance is 1 over omega times XL, or if you happen to know your capacitive reactance, and then your inductance that you want to use is your XC over omega. And as you can see, each one of those can be solved for by simple algebraic properties. So this means if you want to build a resonant circuit, and you then just pick one to start with, either a capacitor known value or an inductor's known value, and then solve to know how much inductance or capacitance to use for the other part. Such as in a Tesla coil, you would want to match up your capacitor with your transformer. Sites like the Geek Group have published tables and whatnot for transformer to capacitor matching. And from there, you can use this simple formula to find out how much inductor you want on your primary for your tank circuit. And for any L and C together, if you know both values, but you want to find the frequency at which resonance will occur, its F sub r irresonant frequency is 1 over 2 pi times the square root of inductance times capacitance in henries and farads respectively. And Z for impedance, equals the total resistance of your series circuit equals R, your resistor value, plus J, remember J from complex algebra, of XL, the reactance of the coil, minus XC, reactance of the capacitor. And when XL equals XC, then it's just R plus, well, those two would cancel out the same value. Let's say it's 10 minus 10, then they cancel. R plus J is 0, well, that's just 0. There is no y-axis, imaginary axis magnitude. So the total impedance of a circuit at resonance is simply the resistance. So in series, at resonance, the reactive components, as you see, would equal just shorts. At resonance, this acts as just a plain old piece of wire, as does the capacitor. The total impedance is simply just R, and that's our little sinusoidal AC waveform indicating AC current source. Voltage source. E is voltage source, yeah. And it should be an I for a current source because it's in parallel. And the at resonance, the reactive components of a parallel circuit are an open connection equivalent, because, well, in parallel we use the admittances, which is Y, so 1 over Y T Y total equals 1 over, well, that equals our Z impedance input, and which is equal to 1 over R plus J, 1 over XC minus 1 over X sub L. Again, when XL and XC are equal, then 1 over, say, 10 equals minus 1 over 10. Well, that's still going to be 0. So we can still get our impedance. That means the total parallel resistance, parallel impedance of these items are going to behave as if those components are not there. And that's the basics of resonance. When you get the most current flow, or the least amount of voltage drop across the elements, your signal either across or through the current through the resistor is going to be at its maximum when resonance, the resonant condition is met. Now, we did touch briefly on impedance just now. Let's go a little bit more over that. So impedance, Z sub L, again, is like the AC version of resistance. It has both magnitude and angle. Z sub L, the impedance of a capacitor, is our J, indicating it's on the vertical axis with our complex algebra. It's the J factor of omega times L. It's 2 pi times frequency times L that value on the j-axis. That's all the j means, just which axis is it, imaginary axis, vertical, as opposed to if the j wasn't there, it'd be on the horizontal axis, which it is for resistors. And then z sub c is simply the reciprocal of that formula, except it's c. So this is c capacitance in farads. Z sub c is equal to 1 over j omega c. Z sub L equals just j omega L. So j, vertical axis, Z sub L, the j is in the numerator. Now, remember, the simple mathematical property of any value is that j omega L is equal to j omega L over 1. Any number, 3,942, is equal to 3,942 over 1. It's the equivalent. You can think of any number, any positive whole number, or even fraction, as being part of a, well, part of a fraction like this here. It's equal to its value over 1. It's just a funny math thing. It happens to be useful in this case. So when a value is in the numerator, the j value is in the numerator, then the angle is going to be plus 90 degrees at most for L, for your inductor. Z sub c, j is in the denominator because it's 1 over j omega c. It's the reciprocal of j omega c, which means 1 divided by. So it's going to be negative 90 degrees because the j is down here in the denominator of our fraction. And then z sub r is just the resistance value at 0 degrees. If you remember our old-fashioned unit circle from either calculus or even pre-calc or trigonometry, imagine there's a circle, so the positive direction of the circle to go counterclockwise. There's the j-axis. There is our x-axis, horizontal, it's imaginary number. There's real numbers that we learned in grade school, hopefully. So z sub r, impedance of a resistor, is equal to the resistance of the resistor at 0 degrees. You see, such as 0 degrees, plus 90, plus 180, and 270, and then back around to 360 degrees, which equals, then you're back at 0 again. Impedance of a capacitor is our 1 over j omega c, which, as we just reviewed in a previous card, is the reactance of our capacitor at an angle of negative 90 degrees. If we go clockwise, it's just 90 degrees in the positive direction. I mean, scratch that. In the negative direction here. Then we have z sub L for inductors is j omega L at an angle of 90 degrees in our positive direction, 90 degrees in the negative direction. So now you can see why when we think about resonance, if the magnitude of x sub L is equal to the magnitude of x sub c, and we have our sinusoidal waveform, think about that, which goes on our Cartesian plane here, then if x sub L is equal to x sub c, because they're at these two different angles, they're going to cancel each other out when you apply the angles. Thus, the total impedance of a resonant circuit where XL is equal to x sub c, but they're at 180 degrees apart from each other, then the total impedance of the circuit, Z total, is going to equal just the resistance of the components, which goes back here, ZT equals R plus J XL minus XC. And this is why that impedance of a resonant circuit is true.